Alright, so I've been working on a project lately. I've wanted to create some sort of procedural terrain. The way that I wanted to be able to do that is by specifying several component waveforms and then combine them together somehow to create something that looks interesting. What I have right now on screen, it might look familiar to anyone who has ever Google searched, for example, Fourier transform. Like, you might have seen something that looks like this, and you might have noticed this kind of cool pattern where in each half period you see all these component waveforms where the fundamental frequency there, the orange curve, you see it has one peak, and then the next harmonic kind of has two peaks, and then the next harmonic has three peaks, and then four peaks, five peaks, so on and so forth. Basically, if you add all these up, you'll get something which approaches this or approximates this blue square wave in the image. And the more of these harmonics kind of that you have, the closer the approximation will be. And so I wanted to kind of do something like that just by eye. I wanted to figure it out. So basically, you can see here, just a normal sine wave without any modifications. And then here in the and you can see the one peak in the half cycle, and then in the second one you see that I add a coefficient here to my angle. So I'm basically increasing the frequency by 3, and then I'm dividing the entire result by 3, and then you can see that we've got 2 peaks, and it's all completely centered on the center of the first peak, but you can see 1 peak, 2 peaks in that half period. And then the astute observer, I suppose, will see by here that we begin to deviate from the source material a bit, because if you count the peaks on this one, 1, 2, 3, 4, 5, we skipped 3 and 4. At this point, I went on and did these harmonics, and then I added them up, and then I saw that looked kind of similar to what I was going for. But I wanted to be able to just throw in as many harmonics as I wanted, to see what a high precision approximation would look like, to see if I was on the right track at all. I wanted to be able to have this control over the precision. So I wanted to be able to say, based on this precision constant that I provide, whether it's 5 or something crazy like 500, I wanted to basically be able to generate a sequence of coefficients for each harmonic that would eventually be used to create each component graph or each component waveform, and then add them all together to get the final composite waveform. The way that I did that was with this powerful feature of Desmos called list comprehensions. That's another cool thing about the setup that I have going right now. I'm just focusing on a single list comprehension right now to generate these component waveforms. You could have, any number of different comprehensions to create even more diverse looking, component waveforms. But anyway, I'm just going to focus on the one that I used for this sequence that I was building off of. As I was going here, I kind of saw I kind of saw like what the pattern was leading me to. So like we've got the coefficient on the first one is 1, and then the coefficient on the second one is 3. We could have either added 2 or multiplied by 3 to get to this one, but then we see on this one the coefficient's 9, so we definitely multiplied by 3 to get there. And then once again, we're just confirming what we already know. From 9 to 27, we're just multiplying by 3. So I basically said, okay, in my list comprehension, I want to like multiply by 3 each time, and the way to express that here in this list comprehension is to say 3 to the power of x for x equals, and then 0 to my precision constant, and then that gives us the series that we want: 1, 3, 9, 27, 81, 243, so on and so forth. And then we can crank this up to 15, and then you can see it's following the sequence that we expect, and gives us back a 16 element list. At that point, once we have this list comprehension that generates our sequence of like coefficients for each harmonic, then what we do is we actually like, you know, add them together. And let me just get rid of all this noise real quick. And it's really cool that you can do this in Desmos. Basically, like anything that will result in like a graph of some sort, you can plug that into a sum and then graph the resulting composite. Basically, I have this sum, and the initial value is 1, and then the final value is our precision plus 1, and we're basically just using each value of n as an index into the list that we generated with our coefficients. You know, I could set SQ to any one of these lists. Right now I have it set to the S3, multiplying by 3 each time. We're basically just plugging that value in from the list as our coefficient to multiply by the angle, and then dividing by that same value the final sine result, or dividing by that same coefficient. And then this is the cool part: each one of those intermediary values during the summation is going to be added into the final result, the final sum, and then what you get is that waveform, that composite waveform, with like the cool, you know, almost like, I don't know, it looks kind of like a mountain range to me, which is, you know, interesting. But anyway, I can crank up this precision to something crazy like 25, and I mean, obviously here you don't see too much of a difference, but if I were to keep zooming in, it would be very precise. You would see a lot of detail, but I don't need that much. Yeah, you could see as the precision decreases and increases, you can see exactly the effect that it has. With 0, we got that 1 peak. With 1, we got the 2 peaks, and then yeah, so on and so forth until it gets very detailed. But anyway, by this point, I'm like, oh, okay, so this is incorrect. Even though I've figured out some stuff that was very helpful in terms of like being able to generate however many harmonics that I want. You know, that's all well and good, but I specifically, as part of this experiment, I specifically want to approximate this that I see here with this square wave. And you know, now that I know that what I had here was not approximating the square wave, it was approximating something really cool that I'm probably going to end up using, but it's not the square wave. So how do I generate the coefficients for each harmonic of the square wave? Okay, so let's go back to these two, because these were still consistent with what was here. The 1 peak in our fundamental frequency and then we've got the 2 peaks in the next harmonic up. If you recall, 1, 2, 3, 4, 5. This one we skipped. We skipped 3 and 4. So let's not do that. Let's try and create the harmonic, which has the 3 peaks in the half period. So you can brute force it, like you can literally just say, okay, I'm gonna test every single coefficient, every single possible coefficient after 3. Like for example, 4, sine of 4x over 4, and then that'll give us 1 peak, 2 peak, only 2 peaks, and it's almost like offset a little bit too, but anyway, we can see that it's incorrect. So we can go up to the next coefficient value, and then we see, oh, that gives us exactly what we wanted. And then from there, once again, we can go up to the next possible value, 6, or the next possible coefficient, 1, 2, 3. That still gives us 3 peaks, so that's not right. So then we can go up to the number 7. So that gives us 1, 2, 3, 4. Yep, 4. So that looks right. And from there we can kind of see what the actual pattern is. Whereas the previous pattern, if you recall, was like multiplying by 3 each time. This one, it seems to be adding 2 each time. So like the coefficient here is 1, and then we add 2 to get to 3, and then we add another 2 to get to 5, and then we add another 2 to get to 7. And then so now the question becomes, how do we represent that as a list comprehension? I want to take the sequence, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I want to turn it into the sequence 1, 3, 5, 7, 9, 11, 13, 15, 17. Here, let me see if I can just put those side by side so it makes sense. So 1, 2. Oh god, it's probably not going to make sense. And I want to turn it into 1, 15. Oh gosh, it's already not aligned anymore, but whatever. What you'll notice with this is it almost looks like the values are being doubled, but then after they're being doubled, then we're decreasing it. We're like decrementing it. So it almost looks like 2x minus 1 kind of. So for example, 1 times 2 is 2, minus 1 is 1, and so that gets us the first one over here. And then 2 times 2 equals 4, minus 1 is 3, so that gets us that one. 3 times 2 is 6, minus 1 is 5, which gets us that one. 4 times 2 is 8, minus 1 is 7, which gets us that one. 5 times 2 is 10, minus 1 is 9, 6 times 2 is 12, minus 1 is 11, 7, 14, 13, 8, 16, 15, 9, 18, 17. So that's what it looks like. So let's see if we can do a list comprehension for that. So that would be 2x minus 1. All right. I see that we got a negative in there. Well, let's just do 1 to p. Yeah. So that'll give us a different number of elements than our previous ones, which for this we're just doing visualizations and stuff. It doesn't really matter, but that's just something to be aware of. Like, what is the optimal, I guess, domain for your list comprehension. I guess it's just something to be aware of. But anyway, so yeah, 1, 3, 5, 7, 9. That looks like what I want. So what I can do is I can say SF. Oh, great. SF. So now I have switched to this list comprehension in my little computation here. So now I'm gonna see, is this gonna give me a square wave? Oh gosh, what happened? What happened here? S. Hold on. I'm gonna switch back to this. Okay, so it's definitely working. So now, what is the issue? P plus 1. Oh wait, hold on a sec. Maybe there is an issue with the. Oh, okay. So well, that's very interesting. 0, and then I'll say 25. One. All right. Oh man, that does not look like a square wave. Well, that's something that I'll have to figure out. Okay, so I figured it out. Yeah, I think I just let like an off by 1 kind of error just kind of hang out in my setup here for the longest time. Yeah, I should probably just for simplicity make these 1 based. I think it'll just make everything easier. We can set our precision to 5, and it'll mean that our lists will be 5 elements, and then we can just go 1 to P, and that makes a whole lot more sense for accessing the elements, since the list elements in Desmos are 1 indexed rather than 0. We don't have to do anything weird here, like going from 1 to P plus 1 and stuff like that. Now we're good. So if we go to our square wave, it actually looks like a square wave. So, and then the more precision we throw at it, even more so, it looks like an actual square wave. So yeah, pretty cool.